Hello everyone and welcome. In this video, we will explore the VGG architecture, which was a major advancement in the field of image classification at the time of its publication. We will see what this VGG architecture looks like, how it works, some of its core ideas, and its pros and cons. So without further ado, let's get started. VGG architecture was developed by researchers at the Visual Geometry Group at Oxford University in 2014-2015. The group was collaborating with Google's DeepMind at the time this architecture was developed. VGG in the name stands for Visual Geometry Group. The 16 and 19 in VGG16 and VGG19 refer to the number of weight layers in the models. At the time of its publication, this architecture was a revelation and changed the way researchers looked at and performed computer vision. This is how a VGG architecture in its simplified form looks like. This specifically is a VGG16 architecture. It has 13 convolution layers and 3 dense layers. The blocks A and B were created by us to simplify the architecture and make it easy for you to visualize and understand. As can be seen, the VGG architecture is designed to be both deep and architecturally uniform. This means that it uses repeated layers of the same type to simplify the network's learning process. Each set of convolutional layers, which are key for detecting features in images, is followed by a pooling layer to reduce the spatial size, thus reducing the amount of computation required. Finally, at the end, the network uses dense or fully connected layers as its last few layers for classification. Pretty simple, right? Key features of VGG include the use of very small convolution filters, specifically 3x3 filters, which allowed the network to capture fine detail features with fewer parameters. This simplicity and depth enabled the network to achieve excellent accuracy in visual recognition tasks. Another idea that VGG proposed was that of deep networks. The researchers observed that having more layers or going deeper with smaller filter size improved model performance. They also observed that using larger size images improved model performance. This makes sense, as with more pixels, models can learn the finer details as well as go deeper. The researchers also proposed 2 other ideas that kind of seem obvious now, but were made popular and brought into mainstream by this group in their paper. The first one was regarding ensembling. Ensembling, as we have seen before, is the combining of predictions of multiple models to get an even better prediction. This is because of the averaging out effect. And while it may seem obvious now, the team was one of the first to observe and report this. Another was the idea of transfer learning itself. The team was one of the first to use weights from an existing model instead of random initialization to speed up model training time. The main advantages of VGG are excellent performance on image datasets and a straightforward architecture that's relatively easy to implement and adapt. However, due to its depth and the size of fully connected layers, it can be quite computationally intensive and resource demanding, which might not be ideal for some real-time applications or for devices with limited hardware capabilities. In practice, however, VGG can be optimized to run on smaller, less powerful devices by using techniques like model compression and pruning. To sum up, the VGG architecture has been a cornerstone in the advancement of deep learning, especially image recognition. Its design and its ideas have paved the way for newer, more efficient architectures that continue to push the boundaries of what's possible in machine learning today. And that is all for this video on the VGG architecture. In the next video, we will try out VGG for ourselves using Python and TensorFlow. So see you there.